Generally, if we want to find the domain of a composition, the domain will be the domain of the inner part. So if it's something like f composed with g, that would be the domain of g, along with the values in the range that do not break the outer function. That is, the values in the range that are not in the domain of the outer function. So we would have the domain of g and the values in g's range that don't break f. Yeah, that's really specific, really picky. It makes it sound weird and hard to follow, but we'll see with an example here that it's not quite as complex as it sounds. So for this example, we want to find the domain of f composed with g, where f is 2 over x minus 4 and g is 1 over x squared. So for this, the first thing we have to do is, well, find what f composed with g actually is, where in this case, we would have f evaluated at 1 over x squared. So that would end up being 2 over something minus 4, where the something used to be an x. We're replacing that with a 1 over x squared, which is a truly terrible looking function that we can make a little bit better following a careful multiplication by 1. In this case, we want to get rid of that term. We can also find common denominator, keep, change, flip, but for most people, multiplication by 1 is a bit more efficient in terms of being able to see that. So we'd end up with 2x squared over 1 minus 4x squared. And if you don't believe me that these are equivalent, you can do some of that algebra for yourself. Check. Where in this case, we're starting from a not so terrible spot because the domain of g is just going to be everything other than, well, x equals 0. So we know that one's not going to be in there. And then from there, we need to figure out what would break this thing. What causes this whole piece here to break, which happens when the denominator is 0. So if we want to find the domain, that means we have to find where 1 minus 4x squared is equal to 0, just like we did when we were first talking about this stuff way back when at the beginning of this section. And that's going to happen when x is equal to plus or minus 1/2, which I'm writing as a decimal for absolutely no good reason. I just want to. But if we need to find the domain of our composition here, the domain of f composed with g, that is going to end up being everything up to negative 1/2, because, well, we're actually all good just about everywhere else here. All we have to worry about is the division by 0, which we have 2 cases of, along with the values from negative 1/2 to the problem that we had with g originally, 0. Then from 0 to our other problem, and yeah, this is going to be dumb notation, but that's okay, I ran out of space. Everything from our other problem and on to infinity and beyond. So that's how we would find the domain. Basically just see what things don't work for the inner function, and then see what things end up being a problem for the whole composition, as it were, entirely. Which usually is going to end up being very similar to finding what the problems would be with the outer function. It's not actually quite as bad as that clunky looking phrasing makes it seem. Anyway, that's all we have here for 2.6. Next we're moving to 2.7, where we're going to talk about a really important case with compositions and a really important case with a construction that, for our purposes, isn't going to seem very deep, but actually goes pretty far in terms of how you can define relationships in math outside of just being functions in terms of a thing called the inverse. That's what we're getting in 2.7.